Ladies and gentlemen, we'd like to welcome Mr. Max Kriegleder and his presentation on the distributed flight array and the benefits and requirements of cooperation in multi-agent systems. Thank you.
Yes, thank you. Hello, everybody. Yes, my name is Max. I'm from ETH Zurich. I'm a PhD candidate there. And today I will talk about cooperation in multi-agent systems and the benefits of this. I will first present to you two motivating examples that exemplify the benefits of cooperation, and then I will turn to the distributed flight array, which is a modular robotics platform. You see here 4 of these modules lying around already. And I will show how these agents cooperate to achieve common tasks. So let's look at a first example. Here in this picture, you see multiple unmanned aerial vehicles, also known as drones, that cooperate to achieve common tasks. One of these tasks can be mapping a large area for search and rescue operations. Just think about, for example, a wildfire, and the task is to quickly find what regions are actually affected to rescue then people from these regions. Another task can be scanning high-risk sites rapidly. Think about, for example, Fukushima, where some catastrophe happened, and you want to be able to scan this area quickly, but you cannot access the area manually. The third task could be creating communication networks over large areas. Think about deserts, mountains, places where you just can't access it with regular networks, with regular cellular networks. For all these tasks I just talked about, we can identify 3 things. We want to be fast, we want to be robust, and usually we want to work on a large area. Things a single agent would not be good at, or not as good as multiple agents. A second example where cooperation is very beneficial is for autonomous cars. I'm sure you have all heard of the Google driverless car, and this project has been very successful over the past years. It has actually been driven over 500,000 kilometers accident-free on regular roads, and many big car companies such as Volkswagen and Volvo are involved in similar projects. So it's becoming more and more conceivable that in the midterm we actually see autonomous cars, at least in very structured environments such as highways. And you can now imagine the impact on safety and efficiency. Having multiple autonomous cars cooperating, as you see in this mock-up picture here, we can imagine that safety will heavily increase because of the reduced error that we see today, mainly because of humans doing something wrong. Also, you can imagine how the impact on efficiency. Cars could move in platoons, as is already tested today with trucks. So there's one truck in leading, and multiple trucks are following this leader. This will reduce drag and in return increase efficiency. What is enabling cooperating systems in general is sensors, communication devices, and computation. It is becoming more and more viable to actually put sensors, communication, and computation devices in almost any physical device. Most of you will have such a device in your hand or pocket right now, the smartphone. The smartphone has been the driving technology over the past decade, and it has made sensors extremely powerful, extremely cheap and small. The same applies to communication and computation devices. Now, if we have multiple devices that carry such a communication device, we mainly see 2 communication network architectures. One could be a centralized one, where multiple, here these black dots denote agents, are all connected to one central instance. This could be a master agent, this could be a server, you can imagine. On the other hand, there's a distributed architecture. In this architecture, agents only communicate to their immediate neighbors, but not to a central instance. Now we have the sensors, the communication, computation at our disposal, and we also have communication networks. And what we now wanted to do, because we believe in the next generation of cooperating multi-agents, there will be several challenges, and we wanted to test these challenges on a real-world platform, which is the distributed flight array. The distributed flight array consists of multiple agents that join on the ground and then coordinate their actions to take flight, which you see in this mock-up video here. One of these agents, the same you see here on the stage, consists of several parts, and I will highlight them for you. So first of all, there's the chassis. The chassis is 3D printed. It's made of an enduring plastic. And 3D printing has the advantages that we can tightly integrate all the components and do things that were not possible before. We also have 3 drive motors, which you see here. They're omnidirectional wheels, so we can highly maneuver in all kinds of directions with only these 3 wheels. In the middle, you see a propeller and a flight motor. This combination can produce enough thrust that a module can lift itself off the ground. We see also electronics. They're integrated up here. For computation, there's a 32-bit microcontroller that runs at 72 megahertz. If you compare that to your today's smartphone, it's ridiculously fast in comparison. But still, we'll see some quite cool tasks that we can achieve with this. In terms of sensing, we have a rate gyroscope. The rate gyroscopes tell us the angular velocity of an agent. In addition, we have an infrared distance sensors. It will tell us the distance to ground. On the sides, we have 3 push pins. You will recognize them if you come up later to the stage and look at them. You will recognize them if you have a Mac computer. It's almost the same connector to power your Mac computer. With these transceivers that are equipped on each of the 6 sides, the modules can communicate with each other. The modules can also communicate back to a server using this wireless transceiver. It's almost like your Wi-Fi chip in a computer. Slightly different protocol. What it is much more robust, but the bandwidth is much lower. And what we also have are magnets on the side. So if I take these 2 modules here, you see that they stick together, but if I rotate them, they could become apart. I'll just repeat this. So the magnets are strong enough to hold the 2 modules together in the lateral plane, but if I rotate this, well, it simply falls off. I will talk about this later. Just a few acknowledgements. This platform was completely developed at our institute. The platform was originally envisioned by Professor Raffaello D'Andrea. He envisioned the platform in 2008 and was then involved in all different aspects still until today. The project was led over the past 4 years by Ray Ong. What you see today is mainly the outcome of his PhD work over the past 4 years. In order to create such a platform, you always need technicians, and that was Mark and Igor, both led the electronical and the mechanical design. I joined this project in 2010, I believe. I worked on distributed estimation. I'll talk about this later today. And among that, there were many other students involved that I cannot name now, but you can imagine it takes several people to do something like this. So now let's imagine several of these agents connected. You see 2 of them lying here. Let's say we have 6 of them connected. I will discuss how a module can actually figure out where it is in this assembly and how this will then become beneficial. That's in the second part of my talk. So let's take a closer look at this. This assembly of 6 modules, you see that each of the modules carries a unique identifier. You can think of this like it's an IP address. It's unique in the array and determined beforehand. There could be some central instance that just assigns the numbers. It could be the MAC address. You think of it. These agents, they communicate to the direct neighbor. This is indicated by the red arrows. And what we first need to know is what is the actual network topology. And commonly in literature, this is called the Laplacian matrix. I'll walk you through this in a second. What it is, the Laplacian matrix, some of you that have worked with networks might have seen this already. It just really captures this network topology. So each of the rows belongs to the agent that carries this number. So row 1 belongs to agent 1, row 2 to agent 2, and so on. You get the idea. On the diagonal, so if I go here, on the diagonal is indicated how many neighbors one agent actually has. So if we look at agent number 1, it has 2 neighbors, neighbors 2 and 3. And well, that's what we see here in this Laplacian matrix. Take another agent, number 6, it only has 1 neighbor. Well, here we go, that's what it is. Then on the off diagonal, whenever you see a -1, that means this agent is actually connected to the one that belongs to this row. So here, row 1, you see 2 and 3 have a -1. Well, that belongs to these 2 guys. So it is a very simple, nothing so special about it, but the cool thing, it captures the whole network topology. And how do the agents actually come up with this Laplacian matrix? Well, it requires only a 2-step sequence. The agents first determine their immediate neighbors. We call them one-hop neighbors. You can easily do this if you imagine that each of the agents constantly sends out, hello, I'm here, and just tells its neighbors. If all of these neighbors do this, then you just listen to these packets, and whenever you get this, well, you understand I must be connected to this guy. Once you have that, you flood the entire network with this neighbor list. So once agent number 1 found out that it's connected to 2 and 3, it tells everybody. And how this is done? Well, 1 tells 3 and 3 passes on this information. It's not scalable because the more agents we have in the network, well, the more packets are going to floating around. There may be other approaches. You can think of a server. You just tell the server your neighbor list, and then whenever you want this information, you just download it again. But for our case, we regularly work with network sizes from 6 to 10. That's still fine. Once we have this Laplacian matrix, we can easily figure out where other agents are actually located. And when I mean located, I mean actually at what distance or at what specific point they are in a local coordinate frame. So let's look at agent number 1 again. Agent 1 can easily find out because it knows it's connected to agent number 3, and it also knows on what side they are connected. I've not shown this in the Laplacian matrix, but you can imagine you can simply add this information. So agent 1 knows exactly that it's connected to agent 3 on this side, and because the physical parameters are also known, each of the agent knows exactly how big they are, it can easily find out that in a local coordinate frame, agent 3 must be here. Then in order to find out where's agent 4, well, it knows that 3 and 4 are connected on exactly this side, so they know that agent 4 is located with respect to agent 3 relatively here, and then you just add what you already know. Each agent continuously does this until it knows exactly where all of the other agents are in the network. I've only depicted here these 3 arrows, but you can imagine doing the same for these 2. Once everybody has done this, everybody knows exactly where all of the other agents are. In a second step, this information can be then transformed to a unique body frame. So instead of knowing where everybody else is with respect to yourself, you simply transform this to a unique body frame. This body frame is located at the center of mass, and it's aligned with the principal axis. If you don't know what the principal axes are, it's not so important. Basically, it's every body has these principal axes, and it's the one where the mass moment of inertia doesn't have off-diagonal terms. That sounds a little bit fancy, but basically what it is, if you have a box, the principal axis would be, in this case, like this, that, and in this direction. It's not so interesting if you don't know it, but it's important because we want to relate to one unique body frame, and everybody should relate to the same one. So, just to wrap up, we have here a body frame. It sits at the center of mass. It's aligned with the principal axis. Everybody knows where it is, and everybody knows where all agents are with respect to this. So, this is the key thing that you should understand until now, and now we look at what cool things we can do with this. So, once we know where they are, we can achieve coordinate driving. These two modules know exactly where the others are, the same for these 6 guys, and they can now cooperate and drive together. I show what happens if they don't cooperate in a few minutes. Also, they can take flight. Each of the modules knows exactly where it is, and they can fly. So, for the remainder of my talk, I will walk you through how we actually achieve coordinate driving, coordinate flight, and also how we can use the information that each of the agent knows where it is in the array, how it can actually estimate the tilt of the vehicle using a network of distance sensors. I introduced the distance sensors earlier. So let's start with the coordinated drive. This is just a mock-up of a module again. I'll walk you through all the description here. So basically what you see, you have a module frame that's denoted by these 2 arrows here. Each module knows where the first wheel sits exactly with respect to this module frame. So there's an angle theta, that's just a design parameter. We could have placed the wheel also here. We decided to put it here. This is, I think, 15 degrees or something like this. Then the second thing to note here is the distance, d, that's also a design parameter, in our case approximately 12 to 13 centimeters. Then the second wheel and the third wheel, they're just 120 degrees separated from this. Why is this important? Let's say I want to drive one of these modules with a given velocity in, let's say, only the x direction. Well, I need to transform this desired velocity to actual wheel velocities. And how this is done? Well, here is a transformation matrix. This is the desired velocity that I want to achieve. This is simply a mapping that only depends on these design parameters that are all fixed for all time. And the outcome is then 3 wheel velocities. So given a desired x, y, and rotational velocity, I can easily find out what I actually have to command these wheels so that they turn appropriately to actually go in the direction with the velocity that I wanted. Just to give you some intuition, let's think about I just want to rotate on the spot. Well, naturally, and that's actually the truth, you would want that these wheels all spin with the same velocity, all in the same direction. What will then happen is we'll just rotate on the spot. Let me show you that. I hope you can still hear me now. So, let's first look at this guy. So I just said I just want to rotate with a given velocity. So this is what I do here with the instruction controller. I simply send commands over this Wi-Fi link to the model and it rotates. So I can command it to rotate in this direction. But I can also if I put them together correctly, so for both the link now right is this direction, all that looks nice and natural. Forward is the same thing. But if I do now exactly the opposite, then they have some issues. If I can try this one here. It doesn't feel so nice anymore. If I try this again. It feels much nicer because they are actually aligned. If I now rotate them again, they don't know that they're connected, so it feels bad to them. Or it feels bad to me. So let's now look at how can I actually achieve driving an assembly of modules. And now it comes to play what I discussed earlier in the first part of my talk. It's important that a module knows exactly where it is with respect to the frame. Well, this is what we determined earlier. This is still this body frame. And now I'd rather want to command the entire assembly. I want to tell the assembly to go in a certain direction, but I personally don't want to worry about each of the modules individually. I don't want to command each of them depending on where they are. So let's look at the kinematics of this. Again, we have a desired velocity. This is now for the entire assembly. So as before, we have an x velocity, y velocity, and a rotation. And we have some mapping that actually maps this then to a given velocity for one of the modules. This mapping only depends on the location of a module and the rotation with respect to this body frame. Of course, if I change the topology, then this will change. But once the topology is fixed, this is a fixed thing, and this is easy to compute. So all of this again happens on board. Could we show this? So they know where they are. Since we need to change them back to the they communicate with each other. And now I can place them anywhere I want. Once I connect them, they use the transceivers to figure out topology, so they know exactly who's connected to who on what side, and I can drive them in concert. And add another one. And again, me, I can drive in the direction. And to me, as a user, I only need to look at it, and I tell the device to go to turn, and each of the modules does what it's supposed to do. So you can imagine intuitively, if I rotate, the modules that sit on the outside need to rotate faster than the ones on the inside, and they handle this for me. All right. So let's take one step further now. Now let's go into 3D. What I've shown you so far, that was all in 2D, that was driving. But now let's actually look at how can we control any flight feasible configuration. And what I want to emphasize before this, a single module cannot fly on its own. It's much like a helicopter without its tail rotor. If I spin up a propeller, let me show you this again. If I spin up a propeller, the chassis pretty much spins around the propeller, and also once it's tilted, there's no way to come back because the propellers are fixed pitch. That means once you're tilted, you won't be able to recover. So we need always at least 4, and then we can control all degrees of freedom. That's tilt in this direction, tilt in that one, yaw, and also the distance to ground. Just a little bit of notation to make sure we are on the same page. So this is the body frame you should be familiar with by now. I've been talking about this. So the body frame is fixed to the assembly. Again, it's located at the center of mass and aligned with these principal axes. And I can determine the state by relating it to an inertial frame. And this inertial frame that sits somewhere on the ground and that's fixed there. And I can describe the position of this device once up in the air through a vector x, y, z. So z would be the altitude and x and y would be somewhere in the lateral plane. I can also describe the orientation by a set of 3 angles. They're usually people that work with quadrotors or other kinds of flying vehicles. It's called roll, pitch, and yaw. Basically what it is, it's 3 rotations about this inertial frame in exactly this order. So you first would rotate about the one axis, then over the other one, and then the third one. And what you end up with is exactly this description of how this vehicle is currently orientated in space. Once we have this, we can determine the flight dynamics. This looks fancy at the beginning, but it's quite simple. So what we do here is we linearize everything about hover. Hover is when the vehicle sits at a certain spot in space, it's not tilted and simply floating there. That's what we call hover. And in order to achieve this, of course, the propellers have to counteract the weight of the vehicle. And if they do this, then it floats there nicely. If they do this and the vehicle tilts slightly, so either this beta changes or this gamma changes, then, well, it will slightly drift to the side. I think you can imagine this, and it's exactly scaled by the gravity constant. Because in order to sit here firm, the propellers need to produce exactly gravity to do this, but if I tilt it then slightly, well, it will just float to the side. If we look at altitude, well, that's simply all the thrust that the propellers produce at the moment summed up. So if I increase this a little bit, the entire vehicle will go up. If I decrease this, the vehicle will slightly go down. Then for the 2 tilt degrees of freedom, this is simply the thrust scaled by the distance of the module. So if you look at a module here that's far away, if this produces a lot of thrust, of course the body will rotate. And the last one here, this is some constant that maps the thrust to a torque. So you saw before that if I spin up one of the propellers, the chassis will start rotating against it. That's exactly what is written here. So if all of the propellers spin up, and spin in the one direction, then the body will counteract in this. So that's why we have propellers that spin in the one direction and propellers that spin in the other direction. If we have exactly an equal number of both and they all produce the same thrust, the vehicle will not do anything. If the ones that spin in the one direction spin up a little bit, the whole body will rotate in the one direction and likewise for the other direction. So to sum up this, here we have a very natural and easy set, because it's linearized, of equations that exactly tell us, well, what happens if I spin up one of the propellers, depending on what module it is and where it is in the array. So you get the idea again, it's somehow related on where am I in this assembly. This is simply summing it all up in a nice form. So it's with matrices. Here in this, it again captures where are the modules and also how much torque do they actually produce if one of the propellers spins up. This is some mass properties, so this is the mass of the entire array. That depends on how many modules are there, and the mass moment of inertia. It's simply how if I apply a certain torque, how likely it is that it will rotate. And these are simply the thrusts that each of the propeller produces. So what we want to do now is we want to control these 4 degrees of freedoms. We want to control that the vehicle goes up to a certain altitude, sits there, and also that it doesn't rotate. And we can do this by simply designing and choosing the appropriate amount of thrust, which is denoted by this vector u here. And what we decided to do is we wrote U as a combination of a matrix Q times this vector F here. And we chose this Q. If you remember before, P just had all the positions of the modules stored in a nice matrix form. And we simply choose the Q such that we have the identity matrix in the end. So we can compute it once we know where all of the modules are in this fashion. Once we have this, well, what we can do then, we can prescribe a function for each of the 4 degrees of freedom that we want to control. So here in the first one, let's just look at the first. That's altitude. That's the easiest to grab again. It's just how high am I? If I'm too high, I want to decelerate and go to a lower altitude. Same thing if I'm too low, I want to go up to a higher one. That's exactly captured here in this function. The first one is a measurement of how high I am. And I compare this to an actually desired altitude. So let's say I want to hover at 1 meter, but I measure, so this would be 1 meter. If I measure it, I'm at 1 meter 20, then this function somehow has to capture this and decrease the thrust such that I go lower. Then you see this one here. This is simply the speed we currently have in the altitude. And that's also the measurement. What you want to do, you don't want to go from 1 meter 20 directly to the 1 meter. You want to have some damping in there. So if you go too fast, this function should somehow take care of this and not decrease the thrust too much. And when I say the function should take care of this, for this you have these 2 parameters. The first one that defines, well, how bad do I penalize the difference between the desired altitude and the actual altitude? And this damping factor penalizes if I go too fast, what should the propellers actually do? I'm not going to discuss this. This is exactly the same thing for roll, pitch, and the yaw. So basically all you should remember here, what we can do, we can compute the propeller speed such that we can, for each degree of freedom, prescribe a certain function that tells us if I'm a certain distance away from where I actually want to be, what should the propellers do that I arrive where I originally wanted to be. These are simply tuning parameters that go all into these functions, and we tune them. I'm not going to discuss how, but there are strategies to do this that you actually achieve some nice and optimal behavior. Just to sum up what actually happens. So let's say we have some external sensors that can be cameras, overhead cameras. This can be GPS. We have the onboard sensors. I discussed this earlier. We have rate gyroscopes that tell us the angular velocity, and we have distance sensors that tell us how far am I away from ground. We can combine these measurements with a filter. There are many standard techniques to do this. And once we have this, we get a set of measurements. So the actual altitude, the speed, the roll angles and their speed, and also the yaw angle and its speed. We have tuning parameters that we computed somehow earlier. Some strategy. There are several strategies. If you're a control engineer, you know how to do this. And you have a reference. So I tell this thing to hover at 1 meter, 0 roll, 0 pitch, and some yaw angle. And I combine all of this and compute simply this part here. This matrix Q depends on the configuration, and in this function F, all of this combined is integrated. Once I have this, I know exactly how much at this point in time I need to command my propeller to spin, and this goes then into the whole vehicle. So each of these modules individually does all of this, does it on board with its own computer. It may get commands from outside. All of the modules get the same commands, all the same reference, all the same external sensor inputs. They compute this on board, they apply it to their propeller. The propeller spins faster or slower, whatever is required, and then the entire vehicle reacts to this. And once the vehicle reacts to this, it will show some certain output, which is then again measured by the sensors, and you just repeat the whole process again. So this is just to sum up the entire strategy. What is important to understand, I just repeat it. We have sensors that are on board, we have computers that are on board, and we send it something, but all the modules receive the same input. Then locally and on board, they decide what to do, and they apply the right thing. So let's look at how this actually can look in a real experiment. So here we have 4 of them. They are combined in what you probably know a quad rotor configuration. Here we already changed the shape. So here now we have 6 of them, another 6 in a different configuration, and you get the idea. We can try and experiment with multiple configurations. All the modules need to know where they are with respect to this body frame. I repeated that a couple times already. In this case, they all get measurements from overhead cameras. You can think of it like a fancy GPS. But pretty much that's what's happening here. This configuration is very interesting because it's almost impossible to fly. It's only this agent that sits here that makes this feasible. If you imagine that this agent was already also sitting here and that it was a line, then we would not be able to control this anymore. If this line would rotate along its long axis, there would be no way to come back from this. It's only this one agent that makes this possible. Same here. This is even, I would say, yeah, fancier. So now we go up to 10 modules. And here even 12. The nice thing, again, an agent only needs to know where it is. So it doesn't matter if we fly 10 of them, 12, 20, 100. It just takes probably more time, as I said in the beginning, it probably takes more time that a module actually finds out where it is, because it has to compute this now 100 by 100 Laplacian matrix and then find out where everybody else is, transform this, and so on. You get the idea. So that's the part that's not scalable. But once a module knows where it is, it doesn't matter, and we can fly 100, 1,000, and so on. Now to a even more advanced experiment. So I've shown you I can assemble these agents on the ground. I can then drive them. I can stick another one on them. I've shown you an experiment where we've flown very different configurations. Now the idea is, well, what if 2 of them join in the air? And this is what you see in this experiment. We have 2 of these so-called quad rotor configurations taking off. Both of them fly. Both of them are tracked by the cameras, and they're completely separate. They're not aware of each other. But then suddenly they snap into each other with these magnets, and as soon as they connect, they realize that there is now a different configuration. So they quickly tell all of their agents, all of this in a second. So they quickly tell everybody else that they have new neighbors. They flood the network with this with this information, and everybody quickly recomputes where it is with respect to this new body frame, and then they can fly. Let's just look at this again. So until they're not connected, they do what they're supposed to, but they constantly monitor, do I have a new neighbor, do I have a new neighbor? And once they find out that they have a new neighbor, they quickly flood the network with this information, recompute everything, and then continue to fly. Here I then tried to land it. I hit the wrong button. Human in the loop. That's what happened here. All right. Now let's look at a last part where we can have these agents cooperate and do something which they could not do on their own. One very interesting part with flying vehicles is to estimate the tilt of the vehicle currently. So we want to know how is it rotated. This is quite difficult. There are no standard sensors to do this. You can somehow infer it with optical flow. You can infer it with GPS. If you know that, if you see that you're constantly drifting to one side, you probably, or you must have a certain rotation, but it's not that easy. But with this platform, we can exploit the distributed nature and use the distance sensors that they all carry. So each of the agents has the distance sensors I described earlier, and this is pretty much a mock-up. This is the ray that shoots to the ground, is then reflected, and tells an agent how far it is away from the ground. I've highlighted here several. You can imagine each of them has such a sensor. Now the idea is, well, if the array is closer to ground, all of them will measure a lower value. But if the vehicle is tilted, then the ones that sit up here will measure a longer distance to ground than the ones that sit to the left of my body. So we can use this sensor network and actually determine what is the tilt of the vehicle. Of course, this assumes that the ground below us is flat. This is simply the kinematic module of this. So again, what we need is somehow the position of a sensor. If it's exactly in the center of an agent, then it's just as before, it's simply the location of the agent with respect to our body frame. Body frame is denoted here. We have the roll and pitch, I discussed that earlier, and we have altitude. Maybe one thing that should be intuitive, we cannot infer the yaw of the vehicle, because it doesn't matter if we rotate this, then the measurements won't change. So this is only dependent on roll and pitch. Then the distance to ground is some nonlinear, funny expression dependent on the altitude of the vehicle, the distance of the sensor from the body frame, and the roll and pitch angles. Now, again, we assume that we are very close to hover. We don't do any fancy things, so the angles will be small, and we can just write this as a linear relationship. So what it is the measurement is simply the distance to ground plus roll and pitch scaled by where the sensor actually sits. That's very intuitive. Now, the sensor model, we won't measure the perfect distance to ground. There will always be some noise, and this is part here. What you usually can do is you assume that this is white noise, that it has a nice distribution, and what you then can do, you can combine multiple measurements, and by combining multiple measurements, I mean taking measurements from each of the agents that is involved in this assembly, and then send them, for example, in a centralized version, just send them back to the laptop, here in this case, a server or a master agent. They simply send this back over a wireless connection, and we then compute the least square solution. If we assume that this noise has certain characteristic, this is actually the best we can do. I just show how this is done. So what we simply do, we combine all these measurements that we received from the agents, combine them in this vector. This is what we want to solve for. We want to know what is the current rotation of, or orientation of the assembly, and how high is it. This is the noise, and then this is the solution. This is standard standard math, and that can easily be computed on board. I've shown here a few experiments, so we used exactly this configuration. And let's first look at this plot here. This was the actual reference, so I had placed the array at 20 centimeters above ground, and then I applied the technique. I grabbed the measurements from all the agents involved, and then compared it to the actual. Applied the linearly squares and compared it to what the truth was. And you see that this fits very well. There's an issue, there's maybe a discrepancy of 1 to 2 centimeters. Then in a separate experiment, I rolled the array at first about 10 degrees, then 5 degrees, -5 and -10. And again, you see here, this is the truth, and this is what I actually get. It's quite good. Usually you can't infer the tilt at all. And here with this technique, we have measures of do the same for the pitch angle. In the very beginning of my talk, I introduced two architectures. There was a centralized one, where all the agents talk to one server or one master agent, but there was also a distributed one. The nice thing about the distributed one is you only need agents talk to their immediate neighbors. So there's no server involved, and there's no server that can fail. It's simply agents. If one of them fails, well, if you have 1,000 of them or 1,000,000, then you don't worry about if one of them fails. And the nice thing is we can apply it the same, or we can get the same result actually we got for the centralized solution, where all of them send their measurements to one base station. They can do all of this on board without this laptop. And the techniques that are called it's average consensus. You can convert this least squares problem to average consensus. I'm not going to discuss the details here, but if you're interested, you can look it up. There are very nice scalable solutions where it doesn't matter how many agents there are. They simply talk to each other, and then they converge to the correct result. And you see this here. Let's first just let's slice it here and just look at this part. So what the color of this denote shows you is the more red, the more the bigger the discrepancy to the actual centralized solution I showed on the previous slide or 2 slides ago. So this distributed solution is an iterative one. So the more iterations we have, the better or the closer we come to the centralized solution. So for a specific configuration, the more we have, the better we get. But this is also dependent on the configuration, and it's dependent actually on the connectivity. Connectivity means if I have a very, very packed network where each of the agents has many neighbors, then we actually get there quite fast. But if I have something that's rather aligned, and I can actually make this align, then the information takes longer until it's dissolved in the entire network. So here it takes longer in comparison to the very packed network. And this is something that is generally a problem. This is a lot of text. I'll parse it for you in a second. This is actually from a workshop. This will happen this year in I think September in Hong Kong. It's an ICRA. ICRA is one of the 2 big robotics conferences. And this is a workshop that asks on the centrality of decentralization in multi-robot systems, holy grail or false idol. And they exactly describe the issues you just saw in the figure. What I highlighted here is decentralization is typically achieved at the cost of local optimality and slow conversion rate. So you saw in the centralized solution, I just grabbed the measurements, put it to my master node, compute it, and send the solution back. That cost me 1 step. It of course involves grabbing all this information, but then I can immediately solve for the optimal solution. The second case I described was this distributed estimation is, well, I have the nice thing that I don't need this main server, but I get to the same solution just by talking to my neighbors. The problem is it takes longer to converge, and it may be only local optimal. And the question they asked now in this workshop is, well, nature shows several examples of efficient and highly dynamic behavior of large-scale animal populations. So you can imagine a flock of birds, herd of wildebeest, all of this, a swarm of fish. They don't have this central entity that they would relate to, and there's no central entity that actually commands each of the fish to do what it's supposed to do, but they only maybe look at their neighbors, talk to their neighbors, figure out what they're supposed to do, and still they achieve very high dynamic behavior. And the question now is, they ask here, why can't we achieve something in robotic platforms? And you see this is a very recent topic. We have seen this also on this platform, and what we found is that a combination of the two, that sometimes sending back information to a central computer, computing everything off board, and then sending it back, may be beneficial in certain cases. In others, we simply want this platform to behave completely distributed and decentralized. We don't want to command each of the agents from a main computer. I'll show one last example of this. So, what we can do with this platform, we can have the agents self-assemble. So this is the mock-up video already. So what these agents do, they now scan the environment. They scan their environment and they use sensors again, they find where are my peers and they try to then come closer to them. So if I remove this guy here, he will try to come back to them. And because of the magnets, once they come sufficiently close to each other, they will actually connect with them. Once they're connected, they will again recompute where am I with respect to this to this small cluster, and then they will act as one. So let's wait until two of them connect. So here, two of them just connected. Now they act as one. They will rotate about their new body frame. There they found another one. Now the body frame, the center will sit somewhere here. They will rotate about this and try to find the other guy. So I disconnected. He realizes that he's disconnected, and he will just rotate about his own local frame again, and then come back to the others. So, just relating this to this, if you wanted to achieve the same with a centralized in a centralized system, I would somehow need a camera that detects all of these agents, then computes something off board, and then commands them and sends it back to them such that they go somewhere. But here what happens is everything is done on board. I don't need the central server, and they just act on their own. So this is an example where it may be beneficial to do it this way. Of course it takes longer. If I have global knowledge, if I have a camera that exactly tells me where they all are, then of course I don't need to do this in this slow iterative process. I simply just drive them all to one point, because I can command them. And yeah, this is sometimes a bit painful to watch because it takes long, but the nice thing is that it's all done on board, and it doesn't matter. Also, if we have 1,000 of them, we don't need a camera that can capture 1,000. So this is nice and scalable. Okay, to wrap up. So I first explained and showed you two examples that demonstrated the benefits of cooperation. That was this network of drones, and this was also the autonomous cars, a fleet of autonomous cars. I then introduced and showed you what the requirements for cooperation are. This is sensing, computation, and communication technologies that we can basically put into any physical device and have then these physical devices cooperate with each other. I showed you then possible communication network structures. One was the centralized one, where they all send back information to the central station, and the central station tells then each of the agents involved what to do. And the second was the distributed one. You just saw the example. And then I showed you our testbed, where we test these things and actually look at what will the next generation of cooperating system, what will the issues be, and how can they be solved. So we looked at a real world problem that combines these challenges. And I demonstrated then how we can actually coordinate these multiple agents and achieve cooperative behavior. And that was first driving. I showed you how to drive an assembly, and I showed you how to fly. And I actually showed you what happens if, that is actually feasible to connect two separate arrays in air. And I showed you a third example that was estimating the tilt of the vehicle, which one of these agents could not do on their own. So thank you for your attention, and I'm happy to take questions. Thank you.
Okay, thank you, ladies and gentlemen, for attending the lecture. Is there anyone that has any questions for Mr. Kriegleder? There.
Okay. So the first question is how can this array handle weights on it? If you put something during the flight, can it somehow get used to the weight, or does it have to compute everything from scratch?
So what they need to know in order to they compute this center of mass, because they know exactly how much a module weighs, and they know other parameters. From this, they know exactly where this center of mass is, so they know how much thrust they need to produce to keep the vehicle level in flight. So if you now, during flight, suddenly add some weight, they don't know this. All they will figure out is that somehow the thing drifts to the side. If you put a lot of weight on the one side, then this will become unstable. What they could learn it over time. So if you have some learning algorithms, then it would figure out, even though I'm producing the thrust that I should be producing, I'm still going to the side, so there must be something wrong with my weight. So if you model that somebody actually later on puts some weight during flight, then you could do this. If you don't have this in this model, this thing will simply go over there and crash the wall. Okay. I hope this answers the question.
Over there.
We saw that models autonomously connected, but my question is which type of sensors do these models use to see themselves? Okay,
so actually I lied, they're not sensors, they are communication devices, they're infrared transceivers. And we kind of misuse them, or we use them in a way such that we can use them as sensors. So on each of the 6 sides are infrared communication devices, and if 2 modules are in line of sight, so if these infrared transceivers face each other, then they can actually talk to each other. So when you saw this thing rotating, so it rotates and scans the area, and as everybody does this, at some point, if they're close enough, they will face each other. And because they rotate and they have a rate gyroscope, they know at what angle they see the different modules. And then because they know that these infrared communication devices only work until 1 meter, well, even though they're very close, he just thinks this guy must be, can be maximum 1 meter away at this angle. If he sees another one, then he sees that. So actually what they know is at what angle they see other modules. They assume that they're the furthest away, and then they compute, given this information, where they should go next, such that they come closer and do not separate from the group. That's the idea.
Okay, do we have any other questions?
Okay, I'm coming. Let's assume we have a situation when all of the agents are distributed. So what's the algorithm that they link together? What's the optimized structure? Is it a line or just more packed one?
So in terms of, if you want to do very aggressive maneuvers, then it's better if they are very compact. Because what I can do if I put them together very compact, then you see this doesn't even break off because there are now many connections.
So it's more stable.
It's more stable, and I can do I could probably do a flip. Whereas if I have this guy sitting here, if I lift this now, he will fall off. So if you ask me to, like, if I get to pick what configuration I fly them, then I would put them in much denser configuration where there's much more connections, such that this thing will be compact and nice.
So their aim is to link so as to be the most stable position.
If that could be the goal? Or
Yeah.
the issue is, you saw that this is a completely random process. They don't know where the other modules are exactly. They can only assume that they are 1 meter away. So there's no way that I could tell them come together in this one configuration. It's random. So for this I would then probably need some camera, and that then guides this one module to now drive over here and connect like this. Yeah, but this would need an additional sensors.
So it's not the most efficient one.
Say it again?
It's not the most efficient one.
Yes.
Yeah.
I mean, it depends on what you want to do. For me, this is nice because I don't have to set up a camera, for example. So if I want to, let's say, if I wanted to use this to quickly scan an emergency site, then what I want to do is I just deploy many of them. They, for example, scan maybe the room, they drive around on the floor, and once they see there's an obstacle, some of them group and they fly over it. For this task, I don't want to install cameras everywhere, so of course then this would be the much nicer solution. If there are other tasks where I want to show cool performance, then of course maybe a camera would be nice. It really depends.
Thank you.
Okay, we'll be taking one last question. Ladies and gentlemen, at 8 o'clock we have a reservation at the Cabaret Cafe. We'd like to invite you there, and Mr. Kriegleder will be there, and he'll be answering more questions you guys are interested in.
I have a question. You used linear approximation for the angles, and at what angles does this approximation get really bad?
It's hard to say. So you say like for the linear approximation?
Yes.
I mean, it depends what you decide is bad. That's whenever you do linear approximation of something. Some people would say 10 degrees is bad. You simply calculate the sine, like plug it in, and then do this approximation, and you see a discrepancy. It's hard to say. It depends what you define as bad, I think. For our application, it's fine. So you saw it up until 10 degrees. We had an error of 2 to 3 degrees. And then, of course, the closer, so what would happen is we would realize that we are 10 degrees, and we would apply the right amount of thrust on all of the propellers such that we come back. And the closer we come back, so we know that we are very off. We don't know if it's 10 degrees or 15 degrees, but we know we at least the direction. So we come back, the closer we come back, the better our approximation comes. So that's the nice thing about this. Because we level. And the closer you are to the level, the better your linear approximation is.
So if you are at a high angle, then we get a better approximation,
Worse.
but we will get the right direction.
Yeah.
So we will get...
Your approximation gets better the closer you are to hover. At hover, your approximation is perfect. At 1 degree, it's not bad, but at 10 degrees, it's comparably worse. But the nice thing is I know that I'm at 10 degrees, and I don't know the exact number, but around 10 degrees. So I come back, and the closer I come back, the better I get. It's a very nice feature here.
Okay, so we have one more question.
Okay. I wanted to ask about the calculations done when working in this distributed topology mode. So, is each one of them doing calculations only for itself, or is there a situation where one is doing calculations for the other?
No, so they're really doing everything for themselves. So once they have assembled, once they know where they are, they actually completely work without their neighbors. You could imagine something like the one measures something, so for example like this tilt estimation technique, then they simply share information. But the computation is always done locally. You could of course imagine, I mean this would be now really like going in the far future, we could have some models that are simply there for actuation, that have very strong propellers, and others that don't have propellers but very strong computation.
So you could kind of make a more heterogeneous platform. The issue, of course, with something like this is what happens if the one with the propeller breaks off, then they're all are screwed. So the nice thing here is it's very homogeneous. Each of them can do everything on its own. If I have 110 of them break off, we can still continue flying.